Okay, so in this chapter, we will discuss the support vector machines, SVM, which is an approach for classification developed in the 90s. And it's in its simplest form, it looks like logistic regression, but in its more complicated form, it allows um, let me see how I say. So what is the main feature of logistic regression? A hyperplane, right? So support vector machine in its simplest form also turns into a hyperplane, but in its non-simple forms, it allows decision boundaries that are non-linear. Okay, so that's the main feature. So in a sense, support vector machine is a is a is a generalization of a simple and intuitive classifier, which is the maximal margin classifier. Okay. So the problem with maximal margin classifier is that it cannot be applied to most data sets because it requires the data set to be um, linearly separable. Okay. On the other hand, the support vector classifier, which is an extension of the maximal margin classifier, um, can be applied to a broader range of cases because it can deal with data sets that are not linearly separable. Okay. So the good thing about this chapter is that we already covered most of the mathematical concepts needed in this chapter. Essentially the hyperplane, distance from hyperplanes, half spaces. This is all what we already covered. So I will quickly go over it just to um, just to review some concepts. Okay, so a maximal margin classifier um, involves hyperplanes and half spaces. Okay, so this is something you saw before, and if you forgot it, I refer you to the beginning of the semester where we spend a significant amount on half spaces and hyperplanes. Okay, so here's an example. In the two-dimensional space, we have x2, we have x1, and then we have this hyperplane, which in the two-dimensional space is just a line. And if you look at this form, there is the intercept plus beta transpose x being equal to 0. So beta, the intercept is 1 in this case. And then you have 2x1 plus 3x2. So 2x1 plus 3x2 is this inner product in 2 dimensions. So that's the hyperplane. And then any 2 points x1 and x2, if you plug it in this formula, if this is greater than 0, then we are in the blue region. If it's less than 0, we are in the purple region. Okay. Now, learning separating hyperplane reduces to finding beta 0 and beta such that when we say separating hyperplane, such that so here for mathematical convenience, our labels are 1 and -1. For logistic regression, we worked with 1 and 0, and this decision to some extent is arbitrary because um, 1 and -1 here only means that these two are different, right? Uh, but it will allow us to reduce these two terms into this one term. So separating hyperplane is a hyperplane that for every point we have, if the label of the point is 1, then this quantity is greater than 0. If the label is negative, this quantity is less than 0. And in short, what we can do is to say, well, okay, if yi is equal to 1, then beta 0 plus beta transpose xi is greater than 0. If yi is less than 1, then the negative of this quantity is positive. And the way to put them together is this. So essentially, we want to find beta 0 and beta such that for all data points we have, yi times beta 0 plus beta transpose xi is greater than 0. That's what we want. Okay. So how do we classify a new test observation? We classify a new test observation in this way. If the new point x transpose beta plus beta 0 is greater than 0, we label the y to be 1. If beta 0 plus x transpose beta is less than 0, then we label this point as negative 1. So what about the magnitude of this? Does it just matter? Is it just sufficient to look at the sign of this quantity, or does the magnitude also play a role? Well, we know from our previous discussions about hyperplanes, about distances from hyperplanes, that the distance of a point from a hyperplane is proportional to this quantity. So in a way, if this quantity can be positive or negative, but the magnitude of it is proportional to the distance from the hyperplane. So if a point is far from the hyperplane, then the absolute value of this quantity is positive. If the and if the x is near the hyperplane, this is small. Okay. So here we have this cloud of blue points, and then here we have the cloud of purple points. We have the cloud of blue points, we have the cloud of purple points, and what we observe is that there are many hyperplanes that are separating hyperplanes. There are actually infinitely many separating hyperplanes. So how are these hyperplanes different? Are they the same for us? Because all of them, all these three hyperplanes um, satisfy this. All of them are separating hyperplanes. The data is linearly separable, so we have many of them, and all of them will satisfy this. So then the question becomes, which of these, for example, which of these three is better? Which of these three hyperplanes is a better hyperplane? Well, the key here is to see which of these three hyperplanes is farthest from the training observation. That's what the maximal margin classifier would choose among all these hyperplanes, because we have infinitely many hyperplanes that are, if the data is separable, right? So we want a hyperplane that is what? Well, what we can do is we can compute the distance from each training observation to our hyperplane, and then the smallest among these distances, because every data point has a distance from a hyperpoint, from the hyperplane. Imagine you look at the smallest distance. So here, for example, this is a hyperplane. This point is closest to it, so this distance is the minimal distance from observations to the hyperplane. We call this the margin. The minimal distance from observations to hyperplane. That's called the margin. On the other hand, for example, this point is also close, but this distance is larger than this distance. Therefore, the minimal distance from the observations to the hyperplane is given by this distance. On the other hand, if we consider, for example, this hyperplane, let's say this hyperplane, then the closest point, I guess, is this one. So this distance, this perpendicular distance is the minimal distance from observations to the hyperplane. Okay, so now then, so the notion of minimal distance from observations to the hyperplane is now understood. Now imagine that among all the hyperplanes that are that separate the data perfectly well, we pick the hyperplane that has the largest minimum distance to the training observations. So that's called a maximal margin classifier. So this is the data that we saw here. It's the same. And then this line here is the maximal margin classifier. And the interesting, in a sense that among all lines that separate these two clouds, this one has the maximal margin, where margin is minimal observation distance from hyperplane. So among all observations, find the smallest distance to the hyperplane. Now, the interesting thing is that the minimal distance between observations and the separating hyperplane always happens somewhere, so that this line is in between these two, so that this distance is equal to this distance. Let's think about it. Why should these two be equal? What will happen if it wouldn't be equal? Let's say, well, what if we just move this a little bit? If we move this a little bit, then the hyperplane will be closer to these 2 points. So the margin will not anymore be this distance, it will be the distance to the blue. If we move this line closer to the red, then what will happen is that the maximal margin will be the distance to the red point. So it will reduce the maximum margin. So the largest margin happens when this hyperplane is in a place such that the distance to the closest points is equal. So this distance is equal to this. So in the training observations, the points that are closest to the hyperplane, there will typically be a group of them. These will be equidistant from the maximal margin hyperplane. This is the maximal margin hyperplane, and this point, and this point, and this point are equidistant from this hyperplane. And for that reason, we call this point, and this point as support vectors. These are known as support vectors. It is essentially this point, and this point that determine this the orientation and the location of this hyperplane. For example, if you take this and you move it a little bit to the left or up and down, as long as you don't move it super close to the hyperplane, nothing will change. That makes this procedure very robust to extreme perturbations, because again, if you move this point anywhere around here, nothing will happen. Nothing in terms of this hyperplane won't change. Nothing will change. In other words, this hyperplane will remain the maximum margin hyperplane unless this point comes super close to it. And that will be a game changer then. So support vectors are observations that support the maximal margin hyperplane. What does it mean to support the maximal margin hyperplane. This is the maximal margin hyperplane, and the closest points to it is this point, and this point. These 3 points support this hyperplane. So a maximal margin hyperplane in a way is a function of small subset of observation. Essentially only these 3 points matter. You may say, then what about the rest? As I said, if we move these, perturb them a little bit, nothing will change. But if, for example, this point these 2 regions are called the margins. As long as the points that are outside of the margin move and don't enter the margin, nothing will change. That's very interesting feature. So that this hyperplane is not super sensitive to the specific values of these points. So separable case for all data points satisfy this inequality. So we assume that this exists. There exists a hyperplane such that for all these data points are classified. Now, given that this is the distance, well, this is not exactly the distance, but this is proportional to the distance of the closest point to the hyperplane. We minimize it over all the data points. By minimizing this remember this divided by the L2 norm of beta. This divided by the L2 norm of beta was the distance from the hyperplane. So in a sense, this is the distance from the hyperplane when your unit is the L2 norm of beta. Again, beta 0 plus xi transpose beta is the distance from the hyperplane when the units are in the norm of L2 norm of beta. Now recall that this distance was signed depending on which side of the hyperplane we are. So when you multiply it by yi, this becomes unsigned, positive, given that we are dealing with the separable case. Now among all these unsigned distances, we are looking for the smallest one. That will give us the maximal margin hyperplane. So essentially, we want to maximize M0 so that all points are this quantity is at least greater or equal than m, and then we say subject to beta L2 norm being 1. Because if the L2 norm of beta is 1, then this quantity will be the unsigned, the distance from the hyperplane, regardless of which side it is. Obviously, when we multiply it by this, and it's greater or equal than m, as long as m is positive, then this is m becomes our margin. So this is an optimization problem. Any statistical learning problem involves an optimization problem. It's either constrained, here we have these two constraints, or it is unconstrained. Typically, it is constrained. And every statistical learning involves minimizing a loss or maximizing a gain. Here, the gain is the margin, the distance from the hyperplane, subject to these constraints that sometimes involve the data, sometimes they don't. If it doesn't involve in the constraint, then the cost function will depend on the data. And here it actually depends because m is the lower bound to these quantities. This satisfies this is about observations are on the correct side. Again, this makes sure that the data is linearly separable. When this constraint makes sure that the perpendicular distance from the hyperplane is given by this quantity. Again, if this is a little bit unfamiliar, I recommend you watch the first couple of lecture videos at the beginning of this semester where we talked substantively about distances from hyperplanes. Okay. Now, when we have this m, we are saying observations are at least m away from the border, and then we say we want to maximize that. We want that minimal distance to be as large as possible. Now imagine this is a data set we are dealing with. First of all, the reason I'm showing this is just to emphasize the fact that most of the times the data is not linearly separable. But something even more important is what I want to say is that even if a separating hyperplane does exist in the sense that the data is linearly separable, there are examples in which a classifier that perfectly separates the data may not be optimal or desirable. Why is that not the case? Why do you think even if the data is perfectly separable, where would cases come from, or what is the intuition or the reason behind which we may say we may say that actually we prefer a hyperplane that doesn't perfectly separate the data. Well, the reason is we want to avoid, what is that word? Overfitting. We may want to avoid overfitting. Okay, sometimes we prefer a non-perfect fit because we want to avoid overfitting. Okay, so another way to look at it is we want a method that is robust, that is not sensitive to individual data points. Okay, that's one of the major reasons why we would want to deal with this. So look at this example. The data is linearly separable, and this is a hyperplane. And I think this is the maximum margin hyperplane. Where are the support vectors here? By looking at this figure, can you tell me where are the support vectors? Well, this point and this point, right? They look like they are equally distant. Now the problem here is that imagine the data remains the same, but we have one extra observation, this one. So one blue one is added here. Suddenly, this single data point will significantly move our hyperplane from here to here. And suddenly, this point, and this point will become our support vector emissions. This is what I meant by robustness, sensitivity to single observations. We don't like methods that are sensitive to single observations because observations are noisy. We have many observations and we want all of them to be important and together important. We don't want one observation to significantly impact the statistical learning method. Okay. So we want more robustness and better classification for most observations. That's the objective of a support vector classifier, which sometimes it's also called a soft margin classifier. So rather than seeking the largest possible margin so that every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, okay, correct side of the margin. This is our margin, right? So rather than seeking the largest possible margin, these are the margins. So that every observation is not only on the correct side of the hyperplane. All of these observations are on the correct side. All of these are on the correct side. So rather than seeking the largest possible margin so that every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, this is the margin, and we want these points to be outside it. Okay, we have the support vectors which are at the boundary of it, but we do not want any points in the margin. We instead, in this case, we're just building on top of these methods, right? A support vector classifier or a soft margin classifier instead allows some observations to be on the incorrect side of the margin, or even the incorrect side of the hyperplane. The margin is soft. Because it's soft, it allows some observations to violate it. Look at this. So most observations, so first of all observations are on the correct side of the hyperplane, right? Blues are on this side, reds are on this side. Most observations are also on the correct side of the margin. However, a small subset of observations are on the wrong side of the margin. Again, this is our hyperplane, and this is our margin, and number 1 and 8 are on the wrong side of the margin. Okay, so let's look at the details of a support vector classifier or a soft margin classifier. See how the optimization problem involved here is different from this one, which was a maximal margin hyperplane. So how do we find the maximal margin hyperplane? By solving this optimization problem. So now we want to adjust this optimization problem a little bit so that most of the observations are on the correct side of the margin. However, we would like to allow a small subset of observations to be on the wrong side of the margin. Now, when we hear this, a small subset of observations are on the wrong side of the margin, we like to allow that. We allow some observations to be on the incorrect side of the margin. Then this some observations, the intensity of this thing that we allow is an extra parameter, right? And that will play the role of a hyperparameter that we later will set using cross-validation. But let's just look at this. Let's look at this for a second. Let's look at all the details here and see if we can figure out what this is supposed to mean and what it does and how that is different from the previous one. The first thing that is similar is that M is there. What is different now is that instead of just optimizing everything over beta 0 and beta, we have these epsilon 1 to epsilon n. So for each observation, we have an epsilon, which is called a slack variable, and Let's see what it does. Okay. So where does it play a role? It plays a role here. So instead of dealing with m, which is a margin, we are saying that the distance, so because the norm, L2 norm of beta is 1, this will still be the distance from the hyperplane. And we allow that to be slightly, m times 1 minus epsilon. Epsilon is going to be positive. Epsilon, if it's less than 1, then this quantity is positive. If this quantity is positive, that means that the point is on the correct side of the hyperplane. Again, if this quantity is positive, when is it positive? If this quantity is positive, then this quantity is positive. And when this is positive, the point is on the correct side of the hyperplane. When is it positive? When epsilon I is less than 1. Essentially, when epsilon I is between 0 and 1. And then here we have another parameter, C, which is a non-negative tuning parameter. And it's saying these slack variables, they cannot be larger than something. And that something is determined by C, because we remember when I said that, what did I say? I said that we allow some observations to be on the incorrect side of the margin, or even the incorrect side of the hyperplane. Okay, so the intensity of this allowance, if you allow me to say that, use that expression, the intensity of how much we allow this to happen is determined by C. How can we see that? If C is 0, is non-negative, right? Then all the epsilon i's need to be 0, because epsilon I is positive, and the epsilon i's are, when they're 0, then essentially this optimization problem, when C is 0, this optimization problem, reduces to the original we had here, right? And what was this? This was the maximal margin hyperplane, right? Like this hyperplane here, or this hyperplane here, right? So support vector classifier, which is supposed to be more robust, is defined in this way. But if C is 0, it boils down to the previous case. Okay, so let's spend some time, and this is essentially a lot of things that I said are summarized on this slide. So epsilon I is non-negative, and there are 3 scenarios. If epsilon I is 0, observation I is on the correct side of the margin. Correct side of the margin also means correct side of the hyperplane, right? It means that the point, not only is it on the correct side of the hyperplane, but it's also at least m away from the hyperplane. Okay. Now, when epsilon I is between 0 and 1, then this quantity is still positive. In that case, observation I violates the margin, but it's still on the correct side of the hyperplane. Now, when epsilon I is greater than 1, observation I violates the hyperplane, but it's also on the wrong side of the, violates the margin, but more importantly, it's on the wrong side of the hyperplane. So essentially, any data point for which epsilon I is greater than 1 is on the wrong side of the hyperplane. So by using C here as an upper bound to this summation, we are saying that we allow at most C points to be on the incorrect side of the hyperplane. Okay, so the C is a tuning parameter. Another thing that I said that I didn't say, because we did not really talk about optimization, and I think we should, but there is not enough time because there's so much material, and optimization is a little bit technical, but we need it, especially when we move to deep learning. If we move, well, we will. And in deep learning, it is important because there are different options. You can choose different ways to optimize your loss, and they will have different consequences. But here, it's not so much important because this problem is a convex problem. It has a unique solution, and there are very fast convex optimization packages and algorithms written to solve convex optimization problems. So essentially, this problem looks a little bit complicated, but with a little bit of math, it can be reduced to a standard convex optimization problem. The convex optimization book that is free on the public domain, and it's part of the syllabus. If you are interested in this topic, it's a great source, and I just leave it at that. So you can go there. Okay. So tuning parameter C, I said, bounds the severity of the violence. If C is 0, there is no violation, right? Maximal margin hyperplane, if separable. And here's again the same thing, which I said again before. I just leave. I'll just let you look at this for a minute. Take your notes and think about it, and then I will move forward. Okay. No more than C observations on the wrong side. We talked about this. Observation Y on the wrong side of the hyperplane. C is chosen via cross-validation. So if C is small, then the number of observations that are on the wrong side becomes smaller. Therefore, the classifier highly fits the training data. So small c means more complexity, right? Small c means smaller training error, right? Smaller training error means a tendency to overfit. Not necessarily, but we are moving in that direction, right? Large C fits the training data less hard, allows some violations. So, obviously, what's the right C? We chose it using cross-validation, but these are the two extremes. Okay. So I just wanted to I mean, we talked about this robustness. I just wanted to emphasize it again. I mean, I think these sentences are very useful. Observations lying strictly on the correct side of the margin do not affect the support vector classifier. We talked about this, right? And what it means is correct side of the margin, like 7 and 10. If I move 7 and 10, like if I move 7 closer to 10, nothing will change. As long as 7 remains on the correct side of the margin, the classifier will not change. The moment it gets in the margin or on the wrong side, things will change, obviously. But as long as it's on the correct side, nothing will change. The same thing for 6 and 4, and maybe 5, yes. As long as they remain here, we can just move them around. We can just drag 6 to here. Nothing will change in terms of this hyperplane. That's what we mean by robustness. Whereas LDA, you see, all of them are looking, LDA is looking for an hyperplane, logistic regression is looking for an hyperplane, support vector classifier, soft margin classifier is looking for a hyperplane. All of them are looking for a hyperplane to separate the data, but each of them does that using a different loss function, and the loss function expresses what they care about, right? And in the end, all of them will probably give you similar hyperplanes, but slightly different. But I just want to emphasize that even though all of them are looking for hyperplanes, because their cost functions is slightly different from each other, therefore, the results will be also different, and that's why they're just totally, I mean, they're called different methods, right? And the bias variance trade-off, as I said here. Small c classified that highly fits the training data. That means the small c means large variance, small bias. Large c less variance, more bias. And here you can see that what happens as we, well, you see the margin is getting smaller and smaller from here to here, and then here, and then here, right? So 1, 2, 3, 4, right? So is C increasing or decreasing here? Is C decreasing or increasing here? Is the C larger here or is the C larger here? Okay, so I end this video lecture at this point, and I answer that in the next video lecture, and we will continue with the second part of support vector machines together with some R examples. Thank you.